So thank you so much for MR Resources for this invitation. And I have to say, after a year of Zoom meetings like this, Dave Rice and Dan Iverson and Lima out on the beach before sunrise at Asilomar is absolutely the coolest Zoom meeting I've ever attended. So thank you folks very much indeed for doing this. All right, let's get things in motion here. Very good. So today what I'd like to do is review some things that I think are interesting to know and think about, and also talk about a few interesting and new features that we've added to NMRPipe over the last year or two. And this is a very informal presentation, so if there are any questions, feel free to call out in whatever digital way is available to you. And also during the breakout sessions at the lunchtime break, I'll be in the software group. So if there are specific questions that folks have, or if anyone would actually like to see a little bit of software, by all means, please join in. Last time we gathered the Ivan group, we talked about lots of interesting things, including magnificent lectures available on the NMR Box website. And we're going to hear more about NMR Box from Mark Machevsky of UConn in a little bit. But in terms of what bits and pieces we've added to NMRPipe, these include improved auto processing for bulk collections of spectra, which also means improved auto phasing, automated ways to chemical shift reference spectral data, and lots of improvements to non-uniform sampling spectral handling. We've added automated processing for HMS-IST and Nesta, for 3D applications of the Roland NMR Toolkit maximum entropy reconstruction, and this time we're going to talk about a new approach for reconstruction of non-uniformly sampled Relaxation Series data. Along these lines, in non-uniform sampling, we've also added a new baseline correction method based on iterative soft thresholding. And you'll be happy to know that we have a new version of NMR Draw in development for release before the end of the year. And this 64-bit version will be suitable for the modern versions of Mac OS X. And along the way, our colleague, Luke Arbogast at NIST, has implemented pulse sequences for selective suppression of methyl signals. And we've added on a special use of non-uniform sampling to subtract residual signals from a spectrum. And those were presented at last year's ENC. So today and later on, Mark Machevsky is going to talk about the resources of NMR Box. But something to keep in mind is that the NMR Box folks are always having seminars about software and computation. So keep an eye out for these in your group. And if you like the kind of things you hear from Mark today, and you might be interested to schedule a set of seminars in your particular part of the world, by all means, let the NMR Box folks know about this. So here are some of the new tools that we spoke about last time. In particular, and maybe one of the most useful aspects of software tools for non-uniform sampling that we've added to the software is a graphical interface that allows us to do complete spectral processing of non-uniformly sampled data, 2D, 3D, and 4D, without the need to edit any scripts, and in a format that allows us to easily and conveniently process or reprocess a particular data set with different reconstruction methods and see the results side by side, as you see here. So this software screen was generated directly by facilities in NMRPipe. that let us choose between the different reconstruction methods, which right now are NMRPipe's IST, SMILE, HMS IST, Nesta, and the Roland NMR Toolkit implementation of maximum entropy. And on the way, we have a similar implementation for Vlad Orakov's MDD that we'll have out this year. So here are a couple of things that I think are interesting to know about that we don't hear spoken about enough. And one thing is that when we talk about non-uniform sampling in a casual way, we usually talk about non-uniform sampling in terms of sampling density. Oh, I did this NUS experiment at 50% density, 25% density, and so on. And for casual discussion, that's fine. But something critical to keep in mind is that the effectiveness of a non-uniformly sampled acquisition and reconstruction depends on the number of signals in the data. So that a particular sampling density that is suitable for one spectrum with a given signal to noise may not be suitable for a spectrum that has the same signal to noise, but a different number of signals. And this was characterized by David Donahoe and folks in his group who spoke about what they call a phase transition in the ability to make a good non-uniform sampling reconstruction. And it turns out that this depends on two things. One thing it depends on is that the spectral data must be sparse, which for our purposes we can think of as meaning that the spectrum has more empty space than signals. So that seems pretty reasonable. But the other thing is, and if we think about it, it makes perfect sense, the number of samples that we acquire has to be sufficient to describe the number of signals in the data. So very obvious, but the implications are a little surprising. So for example, in a 2D data set, if we have 128 points sampled at 50% density, according to a curve like we see here, in order to get a successful reconstruction, we can only have about as many as 12 signals in the densest column of the 2D data. So the restrictions are actually much tighter than we might guess. And I'd like to show you an illustration of this. What you see here are simulations of 4 different versions of a 2D plane from a 3D data set. And each of these simulations has a different number of peaks. In the top left, we have data set that has 378 peaks. And at the bottom right, we have a data set that has only 18 of those peaks. And in between, we have fewer numbers. So what you will see in this slide is an animation of the reconstructions as we go lower and lower in sampling density. So right now, 80% sampling density, everything looks good. 75%, everything still looks good. 65%, everything still looks good. 60, 55, 50%. Now below 50%, we can just start to see artifacts begin to appear in this data with a large number of peaks. 25% density, now this spectrum is unusable. We can start to see artifacts here. 10% sampling density, now this spectrum becomes unusable. Excuse me. Whereas back at 5% density, this spectrum that has only 18 peaks is still perfectly fine. So it's a clear illustration that the ability to reconstruct a NUS spectrum depends not only on signal to noise, but also on the number of signals that there are in the data. And here's a little graphic that shows the RMS difference between a NUS reconstruction and the fully sampled reconstruction with respect to the different numbers of peaks that we saw in the previous example. And one way we can think about this is to think about the reconstruction as a kind of problem in numbers of degrees of freedom. So each peak requires a certain number of parameters to describe it, and we have to have enough samples to account for those parameters. And so if we imagine peaks described in terms of a number of positions and line widths and so on, we can describe a kind of hypothetical parameter count for a given spectrum with respect to sampling density and the quality of a reconstruction. And what we see in that previous example is that we need between 10 and 20 times more samples than we have peaks in the data. Not so surprising, very reasonable. So that's a nice rule of thumb that you can use when building sampling schedules for your particular data. Here's another lesson which I hope you will find interesting. It's a good reminder, which is that different shapes of sampling schedules give rise to different artifacts in the spectrum. And so these days, the most common types of sampling schedules that we see are either uniform random or Poisson gap weighted, and in particular weighted so that we have lots of samples at the beginning and lots of samples at the end. Now, we can tell the effects of a sampling schedule by looking at its point spread function, its Fourier transform. And what we see here are the Fourier transforms of 16 different uniform random non-uniformly sampled schedules. And when you have a uniformly random distribution and you Fourier transform it, you get a uniformly random spectrum. So in other words, the sampling artifact noise of a uniformly random sampling schedule is uniform with respect to frequency. So that's a nice behavior. However, if we have a sampling schedule that is anything other than uniform random, then the sampling artifacts will no longer be uniformly distributed throughout the spectrum. So as an example, here's the corresponding graphic of 16 different Poisson gap schedules that have been Fourier transformed. And what you can see is that the Fourier transform artifacts in the neighborhood of the peak are suppressed, which is useful, but that artifact noise is spread out so that it's more intense elsewhere in the spectrum. So the gain you get on an individual peak may be lost as we increase the sampling schedule artifacts elsewhere in the spectrum. So this is something that's good to keep in mind. And now finally, I'd like to describe a new method that we have for reconstructing data of two-dimensional series that are often used in T1 and T2 relaxation analysis. And in these experiments, we have a collection of 2D planes with peaks that stay more or less in the same chemical shift position and retain their width. But those peaks evolve in a pseudo-third dimension according to some relaxation profile, which might be exponential, it might be multi-exponential, it might be something else. But the main nature of this data is that it behaves like data for which each peak's parameters stay the same at each plane, but vary in intensity in this pseudo third dimension. And the work that we're going to talk about today was done in conjunction with our collaborators at Brown University, Kyle East and George Lisi. And one of the molecules that they've been working on is this domain from a CRISPR-Cas9 protein that we'll see examples of. So the idea behind our approach is so simple as to be almost dumb, which is to say that we can treat this pseudo third dimension of these kinds of relaxation experiments as an ordinary time domain dimension and simply Fourier transform it and reconstruct that data as if it were an ordinary three-dimensional NMR experiment. And by allowing us to treat the entire body of data as a three-dimensional experiment, rather than having to reconstruct each two-dimensional plane independently, we gain the sampling advantage of going from independent 2D planes, where we can usually sample at only about 50% NUS density, to a 3D case where we can sample at 50% density in each of the indirect dimensions, such that the entire 3D reconstruction can be done at only 25% sampling density compared to what we would do to individual planes. And as an indication, here are some examples. At the top here, we have a fully sampled spectrum superimposed with a 3D reconstruction using our new method at 25% sampling density. The two spectra are almost identical. Below it is one of the planes of reconstructions where we reconstruct each 2D plane separately. And as you can see, the reconstructions are much worse, lots of sampling artifacts. That point is borne home by looking at this graph on the right-hand side, which compares on a point-by-point basis the intensity in a fully sampled spectrum compared to the intensity of the corresponding point in the non-uniformly sampled reconstruction. So the points that you see here in blue are the ones that come from reconstruction with our new method. And that reconstruction correlates to a correlation factor of better than 0.99. Whereas if we look at the reconstruction method that's done on a 2D basis, that correlation coefficient is much lower, about 0.89. And those points are shown in pink here. In order to characterize the behavior and performance of this method, and to see which particular sampling strategies and measurement parameters would give the best results, we prepared simulated data that mimics the experimental data that we just looked at. And these simulations include random phase distortions and random unresolved couplings added to each peak to try to make the simulations as realistic as possible. And these simulations are created in a time domain at the same digital resolution as the measured experimental data. And they include synthetic solvent signal. And since this data is measured on a Bruker spectrometer, which distorts data by not properly accommodating the digital oversampling group delays at the beginning of each 1D spectrum, this simulation includes those distortions as well, so that the exact same processing schemes that are applied to the experimental data can be applied to the simulated data as well. And you can see that the simulation is a pretty good mimic in terms of how realistic it looks. And here's the corresponding NUS reconstruction when that data is sampled at 25% sampling. And so what this ability to simulate realistic time domain data means for us is that it's very easy for us to generate data that can be resampled with different non-uniform sampling schemes, but it also allows us to very conveniently create examples where the spacing of tau values in the pseudo third dimension is linear or random or exponentially spaced. And we can see examples of those here. So at the top, we have examples where the tau values in the pseudo dimension are spaced linearly. And if we look at those curves, so what you see here is the intensity evolution of one particular peak in the spectrum. When we use linear spacing between tau values, we get decays that look exponential if the underlying signal is an exponential decay. Whereas if we use exponential spacing in the pseudo dimension, we get decays that look as if they're Gaussian. So these blue curves here. So what does this mean? Well, in our method, we are taking this pseudo third dimension data that looks like this and treating it as ordinary time domain data that we can Fourier transform. And when we transform evolutions that look like this on the left side, we get line shapes that look like this on the right-hand side. And what you can see is exactly what you would expect. When we have data that looks like an exponential decay and we Fourier transform it, we get a signal that looks like a broad Lorentzian. Whereas if we have a decay that looks like it's Gaussian and we Fourier transform it, we get a narrower Gaussian line shape that has transform artifacts, but the line shape itself is narrower. So from the point of view of NUS reconstruction, the Gaussian line shapes are sparser because they're narrower. And so we would expect, in fact, that if we use exponential spacing in the pseudo dimension, we will get better results with this method of reconstructing the relaxation delay data. And when we put this to the test, that's exactly what we see. So here's some examples of comparisons of line shapes from the fully sampled data, the non-uniformly sampled data, with linear and exponential spacing in the pseudo dimension. And while all of these cases work very well, if you look very closely, especially at the planes at high tau values, the non-uniform sampling reconstructions match better when we have exponential tau spacing than when we have linear tau spacing. And we can also characterize these results in terms of not only the intensities in the spectra, but the actual relaxation values that we can extract from the reconstructed data. So what we see in this left-hand side plot is a comparison of the relaxation values that we can extract from fully sampled data along the horizontal axis and non-uniformly sampled data along the vertical axis. And so in black here are results that come from our 3D reconstruction method. And in this case, they have a correlation coefficient of 0.94. And the values in blue are the relaxation values that were extracted from a conventional 2D reconstruction of each of the planes in the relaxation series. And those results are terrible with a correlation coefficient of less than 0.5. So the correlation coefficient here is 0.408. Okay. And at 50% sampling, both methods work very well because 50% sampling is good enough for 2D reconstruction. But at 25% reconstruction, there's a substantial improvement when we use the 3D method. And when we move from a relaxation experiment that has 12 tau values to one that has only 9 tau values, we don't substantially decrease the correlation coefficient between these extracted relaxation values. And so this is about the lower limit, around 8 or 9 planes, in order for this particular method to work out well. So what the summary of those results are is that if we want to use this method to reconstruct relaxation data, we can go down to 25% non-uniformly sampling relative to the typical conventional measurement that we would do. We would like to have 9 planes or more. We would use Poisson gap scheduling, which seems to give slightly better results. And we would space the tau values in an exponential way. So that's an overview of this new reconstruction method. We can perform any of these reconstructions as a single command that can be operated from the command line. So for example, the command here shows what you would use to perform pseudo 3D processing on a conventional, fully sampled relaxation series. And the corresponding commands at the bottom show what you would have to do to perform the same reconstruction, either with NMRPipe's IST, with Jin-Fi Ying's SMILE, or Sven Hebert's HMS IST. And I hope that when we speak next, we'll have an additional command in here to do these reconstructions with Vlad Orakov's MDD. We have built these facilities into the graphical interface that NMR Draw includes for processing non-uniformly sampled and conventional data. Here's the part of the graphical interface that does this, and we have one portion of the interface which we can specify the processing parameters for the directly detected dimension. One part of the interface where we specify the parameters for the indirect dimension, and a part of the interface where we choose the reconstruction method that we'd like to perform. So we can go directly from raw data to a finished reconstruction by any of these methods. All of this is implemented on NMR Box that we'll see more about later. And so that's it. That's my overview. I hope it was interesting, and I look forward to your comments and questions. Thanks so much.
Okay, so turn that volume down. So 1 second here. I'll just mute yours and all.
Okay.
We'll come through this. I hope everyone hears me. Thank you, Frank.
We have an echo.
Yeah. Just a second. Okay, now, thank you, Frank. And
you're welcome.
Questions. Okay, well, if there are no questions.
Dan, or Dave, can we ask questions?
Yes.
Yeah, this is Andy Bird.
Oh,
hey, Andy.
Good. Okay.
Hey, Frank, great talk as always. And
thank you.
Great to see Dan and Dave out on the beach.
Yes.
That is very cool. You know, guys, this is memories and we miss it so much. So this is really cool. And thanks to everyone for doing this. So Frank, I put some stuff in the chat box and it's already been beat around.
Okay, let's see.
But as you were talking, I'll just tell you real quick, because you've already answered it, is that you don't have to sample linearly, that you can do exponential and you get to this. But let me add one very short question to that, which is when you talk about 25% NUS or 50% in each, are you talking about having 18 values and sampling 9 of them?
That's a great question. And no, so that isn't the case. So it means that we would have 9 planes and sample those 9 planes at 25% density each.
In the 2D plane.
Correct.
The 2D gets sampled at 25%. And
Correct.
the third dimension, you take the 9 plane. Okay.
That's exactly right.
Cool. Okay, very cute. Very cute. I like it. Thanks,
yeah, it's simple-minded, and it seems to work okay.
Hey, things that work, you know, what the hell?
Yes, exactly. So there are much smarter methods that folks have devised, but they did not seem to get popularized. So we thought about this simple one and we tried it and it actually worked. So
Very cool.
Yeah.
Thank you.
Okay,
Hey,
so
hey,
one question.
hey, Frank, here's Thomas Schmidt. I have a quick question. Thanks for
Yeah.
the talk. I have a quick question just for conceptualizing about NUS for that sake, or sampling of
Yes.
that stuff. So when I saw the exponential sampling, I kind of automatically thought about a window function. So could one think about that sampling, like the exponential sampling? Would that be similar to like a window function? And then the next question, what I was wondering, does that mean that the area underneath the peak could be also treated as pretty much an area after applying a window function, where the area would be equal to the Fourier transform of the window function or the sampling function itself times the real population underneath the peak?
Right. So those are great questions and observations. And in fact, Thomas, the first suggestion of non-uniform sampling pointed out that an exponential sampling scheme would do the equivalent of a matched filter. So the idea behind the shape of a sampling scheme is indeed related to the ideas of window functions and their point spread functions. I see Dave Rovniak rubbing his chin eagerly. I think he probably has a comment that he would like to add.
If I can interrupt a little bit, just to keep the time, can we have these discussions in this break room?
Oh, okay, good idea. Sorry.
I'd love to hear
Okay.
Dave Rovniak as well, but we do that was deliberately done. The break room were broken into such different topics so that we can have these kind of discussions continue. So I just want to keep the time going.
All right, very good. So thanks for the nice questions, and we'll continue this discussion later.